Hi, in this presentation I go over Dream to Control, Learning Behaviors by Latent Imagination by Daniger Hafner, Timothy Lillicrap, Jimmy Baugh, and Mohammed Nourouzi. This is an overview of the topics I'll be discussing today. First, I'll introduce the problem in the RL agent Dreamer. Next, I'll talk about the latent dynamics model, or sometimes called the world model. Next, I'll talk about how to derive behavior from the latent dynamics through something called latent imagination. After that, I'll discuss actor-critic learning, which is crucial to deriving long-horizon behavior. I will then conclude with the experiments and results. So in reinforcement learning, we have an agent, and our goal is to find a policy or an optimal set of actions in order to maximize its expected sum of rewards. The Dream to Control paper uses the DeepMind Control Suite as a benchmark. The DeepMind Control Suite contains a set of control tasks in a physics-based simulation. Here are some examples. So each of these tasks can be framed as a partially observable MDP. It's partially observable because we are forcing our agent to learn from high-dimensional images as observations, which only gives us partial information to the true underlying state. Given an image or observation, the agent takes actions which are continuous vectors, and after an action, the environment returns a scalar reward. In the first example, the agent is a cheetah, and our goal is to teach the agent to control its joints in a way that gets the cheetah to run. Similarly, for the hopper task, we try to get the hopper to hop. These tasks pose a variety of challenges, including contact dynamics, sparse rewards, and many degrees of freedom. The Dream to Control paper introduces the Dreamer agent, which is model-based, meaning that it learns the latent dynamics of the world. The agent also incorporates an actor-critic architecture. I will get more into this later, but this essentially means that it learns both the policy network as an actor and the value network as a critic. They are both neural networks that learn in a cooperative manner. The agent uses its learned world model to perform something called latent imagination. The main contribution of this paper is that the authors were able to create an agent that was able to solve long horizon tasks. Long horizon tasks are those in which the agent needs to take into account far-sighted scenarios when determining the action to take. This is in contrast to short-sighted agents that only consider what may happen in the next small number of time steps when choosing its action. The ability for agents to solve long-horizon tasks is a necessary milestone if we want to create smarter and more general agents. By learning a world model and deriving behavior through latent imagination, the Dreamer agent was able to surpass all previous agents in every metric. Dreamer is more data efficient, resulting in less computation time required to train the agent, all the while delivering better final performance on the task in the DeepMind Control Suite. Dreamer learns the latent dynamics of the world. To understand what this means, we should first understand what we mean by the true model dynamics. But first, a quick note on notation. We are working in a partially observable MDP setting, so in the following definition, I've decided to use observations O to emphasize that we are not working with the true underlying state. So we can define the true model dynamics as the joint probability distribution of the next observation, O prime, and the reward R, given the current observation in action. One thing to note is that we can marginalize this joint distribution to get two other distributions, the observation transition model and the reward model. The problem lies in the fact that in real-world problems, true model dynamics are often unknown to us, and it is often the case that finding it is intractable to compute. Thus, we instead find the latent dynamics, which won't be a true representation of the world, but rather an approximation of the world that we can learn as the agent interacts with the environment. This can be learned via a reconstruction loss as seen in variational autoencoders. Moreover, this gives us an opportunity to work with lower dimensional representations by encoding our high-dimensional inputs like images into low-dimensional latent states. Working with these low-dimensional latent states frees up precious resources like memory and computation. The latent dynamics allows us to derive behaviors in many ways. For instance, the Planet architecture utilizes the latent dynamics to do online planning. However, the problem with Planet and other architectures is that the imagination horizon is finite, resulting in short-sighted behavior. In contrast, the Dreamer agent utilizes an actor-critic approach in order to learn long-horizon behavior. The latent dynamics also enables us to do latent imagination. So this is an overview of the latent dynamics model used in Dreamer. The latent dynamics requires 4 models, each for the representation, the transition, the reward, and the observation. These models are probability distributions in which the statistics are derived from neural networks. Notice that all of the models share the same parameters theta, which means that these models are learned jointly. Also note that the variable s indicates the encoded latent state and not the true underlying state. So the representation model gives you the next state given the previous state, action, and current observation. Its role is to encode the high-dimensional image samples into a latent representation. The transition model predicts the next state given the previous state and action. The reward model predicts the reward for the given state, and the observation model decodes the latent state back into the observation and is only needed to define the learning objective. The models defined with Q denote that they are an approximation of the true model and are used for latent imagination, which I'll get into later. On the right, there's a lot to unpack, so let's work through it step by step. For simplicity, let's just consider the latent dynamics at a single time step. The blue trapezoid is the encoder, and we can temporarily think of the encoder as a conditionally independent version of the representation model that does not depend on the action or previous state. So given an image observation as input, the encoder gives us a distribution of latent states using convolutional layers. The gray trapezoid is a decoder or observation model that reconstructs the original observation from the latent state using transposed convolutions. However, notice that this architecture is nothing but a variation of autoencoder. Thus, learning the latent states for a single time step is the exact same as training a variational autoencoder. What about the rest of the dynamics? Well, we also have the reward model, which is an estimate of the reward given the latent state. We should note that this reward is the imagined reward based off of latent states and not the actual reward based off of observations. The reward model is a scalar Gaussian with mean parameterized by a fully connected neural network. Now let's consider the full picture by bringing back the temporal dimension and the full representation model. So to account for time, the representation model consists not just of convolutions, but something called a recurrent state space model, or RSSM. You can think of the RSSM as a fancy recurrent neural network with a stochastic component. The RSSM enables latent states to capture the history of all previous time steps. Moreover, our representation model will also have to consider the actions we take, which, like the reward model, is based on the latent states and not the observations. So in the previous slide, we considered our latent dynamics as just a single time step, and we had something that resembled a VAE. And so when we bring back the temporal dimension, we now have something that can be thought of as a sequential VAE. And just to really drive the point home, there's a clear divide between what the agent experiences in the real world and the agent's latent representation of the real world. The latent representation can be thought of as the agent's world model of the real world. So to train a VAE, we would typically optimize the variational lower bound. So similarly, for Dreamer, which is like a sequential VAE, we would optimize the expected sum of variational lower bounds over all time steps. Moreover, since all our models share the same parameters theta, we can learn all models jointly. So first, we have the training objective for our observation model. This is a variational lower bound that optimizes for observation reconstruction from a latent state and has its own KL regularizer. Next, we have the training objective for the reward model, which equates to maximizing the corresponding log likelihood. Next, we have a KL regularizer term for our representation model and transition model. And maximizing this negative KL divergence just says that we don't want these two distributions to deviate too far from each other. Finally, we learn these models together by summing up the variational lower bounds and regularizer over all time steps, and then take the expectation with respect to the representation model. And because we are sampling states and actions from a probability distribution, we also need to employ the reparameterization trick in order to backpropagate through these random variables. So this is our latent dynamics. Let's see how to use the learned dynamics to derive optimal behavior. So first, recall that we have the reward model and the transition model, both of which are crucial for doing latent imagination. And now I need to define the action model, which is used to determine the action from the latent state. The action model is parameterized by a different set of parameters phi. The first step in performing latent imagination is to encode a single observation into a latent state using the representation model. Then from that single latent state, we can imagine future state action trajectories of a fixed horizon using the above models. Just imagining the rewards for a trajectory of a fixed horizon is a decent strategy for coming up with decent behavior. However, we are not yet enabling long horizon behavior, which is the main contribution of this paper. To do so, we first define yet another model, namely the value model, which takes in a state S and is parameterized by another set of parameters psi. The value model is equal to the expected sum of imagined rewards over our latent imagination models Q. And so from each latent state, we also predict the value of that state. Learning a good value model allows us to account for rewards beyond the imagination horizon. Moreover, both action and value models are Gaussians parameterized by a neural net. Okay, so we have both the action model and the value model. How do we train them? Dreamer uses a novel actor-critic method. Actor-critic methods consist of an actor and a critic, which in our case are the action model and value model, respectively. The benefit of learning both models is that they can be learned together in a cooperative manner. That is, the value model acts as a critic because it is used to evaluate the actions made by the actor. The actor can then update its parameters in the direction suggested by the critic. Before I dive into the details of their objective functions, I first need to define the value estimate, V lambda, which is different from the value model. The value estimate can be thought of as the true value function that our value model optimizes towards. The first equation, V and K, estimates the rewards beyond K steps using the value model. The second equation, V lambda, is an exponentially weighted average of the first equation for different K values. This is done to balance bias and variance. The objective for the action model is to predict actions that result in state trajectories with high value estimates. Therefore, we maximize the expected sum of value estimates over state trajectories with respect to parameters phi. Maximizing the sum is equivalent to backpropagating through the agent's latent imagination. This is because value estimates depend on both the reward model and the value model, which in turn depend on our action and transition models. To train the value model, we minimize the expected square difference between the value model and the value estimates over state trajectories. In this high-level overview of Dreamer, we can see that there are three main parts to the algorithm: dynamics learning, behavior learning, and environment interaction. I've covered the first two parts when I talked about latent dynamics and actor-critic learning. The last part, which we do after updating our models, is to add an episode of agent interaction to further increase our dataset. This occurs by sampling an action from the action model for our agent to take. Finally, let's start talking about the experiments and results. The first experiment was to test the efficacy of the latent dynamics. For the context, which consisted of 5 frames, the representation model was used to encode the states and observation model was used to decode the states back to reconstructed images. The next 45 time steps were predicted or imagined using the latent dynamics without the observations. We can see that at about the 35th frame is when the performance of the latent dynamics starts deteriorating. The next experiment is to evaluate Dreamer's ability to perform long horizon behavior by altering the imagination horizon. The figure shows that Dreamer is more robust to shorter horizon lengths. This means that the learned value model is crucial in deriving behavior that considers rewards beyond the imagination horizon. The next figure shows Dreamer's performance on the DeepMind control suite against 3 other agents. A through C and D4PG are model-free agents, and Planet is the predecessor to Dreamer. We can see that Dreamer's average performance is better than all 3 agents, despite requiring 20 times less environment steps than the model-free agents. Thanks for watching.